In the following video, we are talking about the graphs of polar equations. And what we're going to do is we're going to investigate slopes of tangents of these polar coordinate equations. So we're looking at a formula here, and it says to find the slope of the curve r equals f theta, to find dy dx of r theta, what you should do is take f prime of theta, multiply it by sine, then you add f of theta multiplied by cosine, divided by f prime of theta multiplied by cosine minus f of theta times sine. And of course, this all works provided that dx d theta is not equal to 0 at the point r theta. So we're going to take a look at an example, and it says find the slope of the polar curve at the indicated point. Well, we have a function r equal 1 minus sine theta, and I provided the graph here, and this right here is called a cardioid. And why do you suppose it's called a cardioid? Well, think about it. Think about the word cardiac. What are we referring to in medical terms? All right, this comes from the Latin for heart. Okay, so that's where this is coming from. Notice that it kind of looks like a heart. So let's suppose we're looking at the point pi over 4, and let's just say that pi over 4 is right there. Okay, this graph of course is not drawn to scale. If we wanted to find the slope of the tangent at that point, okay, well, we could draw a tangent at that point, of course, but to find the slope of the tangent, what we would do is we would use this formula, and that's what we're going to do in this example. So we have r equal f theta equals 1 minus sine theta, and we're going to evaluate that at pi over 4. So let's go ahead and take a look. The first thing that we need to do is find r prime or f prime of theta, and this is actually not terribly difficult because this is just the derivative of 1 minus sine theta. Well, derivative of 1 is 0. The derivative of sine is cosine, but we have to keep that negative there. So negative cosine of theta is our derivative. Okay. Now that we know that, we're going to plug it into the formula that we were given up here at the top. So let's go ahead and do that. So we're going to say dy dx, all right, is going to be f prime of theta, which is going to be negative the cosine of theta multiplied by the sine of theta, all right, plus f of theta, which f of theta was just 1 minus the sine of theta. All right, and then the cosine of theta multiplied by the cosine of theta, and then we're going to take that and we're going to divide it by f prime again, which again is negative cosine theta, and I'm going to multiply that by a cosine theta. Okay, subtracting 1 minus the sine of theta and multiplying that by the sine of theta. Now, yes, you could go about doing some fancy footwork here with the identities and things like that, but I'm not even going to worry about it. I'm just going to go ahead and evaluate already at pi over 4. So we're going to evaluate this one at r, whatever that r value is, the radius there, pi over 4, okay? So pi over 4 is what we're concerned with, all right? Don't worry about the r there. So let's go ahead and figure this one out. This is negative the cosine of pi over 4, the sine of pi over 4, plus a 1 minus the sine of pi over 4, multiplied by the cosine of pi over 4, divided by a negative cosine of pi over 4, multiplied by a cosine of pi over 4, okay, minus a 1 minus the sine of pi over 4, multiplied by a sine of pi over 4. So we've got it there. Now, yes, you can eliminate some stuff here, but let's go ahead and continue. We're just going to evaluate. The beauty of pi over 4 radians is that this pi over 4, the coordinates are square root of 2 over 2, square root of 2 over 2. So the cosine and the sine are actually identical. And this makes this problem actually really easy, and you should start seeing what's going to happen. You have a negative, of course, the cosine pi over 4 being square root of 2 over 2, the sign being a square root of 2 over 2, plus a 1 minus a sine, I'm sorry, not sine, we're going to replace that with the square root of 2 over 2 multiplied by the cosine, which again is the square root of 2 over 2 divided by a negative, and then it's a square root of 2 over 2 multiplied by square root of 2 over 2 minus a 1 minus a square root of 2 over 2, and then multiplied by one more square root of 2 over 2. So what I'm going to end up doing is factoring out square root of 2 over 2 out of all of this. So let's go ahead and see what that looks like. If I factor it out of the first, I get a square root of 2 over 2 on the outside. On the inside, I'm going to be left with a negative square root of 2 over 2 plus a 1 minus a square root of 2 over 2, just like that. And then I'm going to factor out a square root of 2 over 2 again from the denominator. And that's going to leave me with a negative square root of 2 over 2 minus 1. And then it's going to be actually plus a square root of 2 over 2 because minus minus makes for plus. So let's see what happens now. We can eliminate this right here. Okay, that's the common factor. The negative square root of 2 over 2 in the denominator cancels out with the positive square root of 2 over 2, leaving us with a negative 1. And then if you look right here, this right here has the same denominator. So you end up with a negative 2 square root of 2 over 2, which is just a whole square root of 2 over a whole square root of 2 rather. So you end up with something that looks like this: 1 minus a square root of 2, all divided by a negative 1. And if you simplify this just a little bit to get rid of that negative 1, you end up with a positive square root of 2 minus 1. And this right here represents the slope at the point pi over 4. All right. And like I said, there's really nothing to it. It's just applying the formula. We were really fortunate that we got a really nice value, pi over 4. So it's a pretty good reference from the unit circle. One that you should have memorized. So as always, I hope this video was helpful. And remember, like and subscribe.